Hello, good afternoon, everyone. Uh, First of all, I would like to welcome our expert for today's webinar, Dr. Akash Agrawal sir, respected principal ma'am, and all my dear students. I welcome on behalf of BC Bhagalpur EC department you all in this webinar. So, first of all, I would like to request our principal ma'am to please say few words. Ma'am, please.
Hello, hello,
Yes, ma'am, it is audible. Good afternoon, ma'am.
good afternoon. हेलो इसको डिस्कनेक्ट करो। हाँ, hello, yes. Uh, Welcome Dr. Akash Agrawal in BC Bhagalpur campus by online platform, and thank you to accept for the very special topic of 5G and 6G wireless technology, which is under wireless communication and mobile communication. And very happy my student will get benefited by you, and very much in detail they can know about 5G and 6G by you. I am very happy to uh, say about you to our students. Today's speaker have a very nice profile. He's his research area is also 5G and 6G wireless communication and mobile communication. So definitely, student, you will be benefited, and as well as he did he did already work in different fields, like different projects also. His work experience in is also in very nice, he was the network engineer in Boeing India Private Limited, and their project, very nice project, which is also related to 6G and 5G. uh, One more thing, uh, he has he has um, completed their doctorate in also in same field, and master degree also. He worked as an assistant professor in Beats Pelani, uh, Rajasthan also, that is very reputed institute. So we are hoping कि in 5G and 6G field we will know very specific, very different uh, specific and different uh, knowledge, who is very much required for your project student, and as well as knowledge, and whatever GSM based and communication based Mr. Akash Agrawal. Thank you to connect with us. And for that, Professor Prashant and Professor Pushpendra Dwivedi, thankful for this. He is searching such type of people, and that is useful for us. Thank you once again.
Thank you, ma'am, for this wonderful introduction. If I'm allowed, I can go on with the presentation.
Yes, definitely.
Okay, so I should share my screen first, right?
बहुत सारा उनका बीटेक एमटेक सर्विस.
Uh, is my screen visible to everyone?
Yes, sir, it is.
Yeah, I just request everyone to please go on mute, and I'll be the person who will be doing the talking. Thank you. Thank you, ma'am, for the wonderful introduction. And through this presentation, I will try to be as much explicit as possible in the domain of 5G and 6G wireless technologies. As you have rightly mentioned, that my tertiary education and my bachelor's and master's are also, they're all in aligned and inlined in the same field. So I'll try to be as explicit as possible. I'll begin this. So what I've thought before joining this presentation was that I will give a very brief overview of these technologies, and then given the as you said, that given the status of students doing their project work in the same domain, I will be um, grilling myself or grilling them into a particular domain, in a specific domain, and I'll try and go as much deeper as possible with all the curves and graphs and everything, whatever I can do to make this session a fruitful session. So I'll just begin with the introduction of the topic. Today's topic is 5G and 6G wireless technologies with the NTN perspective. NTN is basically the non-terrestrial network perspective. And one more request to the conveners is that if whenever I'm not audible, just ping me and let me know, because the internet connectivity over here is fluctuating today. Okay, so NTN, I was discussing about NTN perspective. NTN is actually non-terrestrial network. Non-terrestrial network means network related to satellites, to UAVs, and then HAPs, high altitude platforms, and unmanned aerial vehicles as well. So I'll start with the general perspective and overview of these technologies, and then I will push deeper into the NTN perspective, where my research work lies. Okay, so as Madam told, that I am presently working as an assistant professor in the Department of Electronics and Communication Engineering of NIT Patna. And in this online mode, let's see that how fruitful this session can be. Okay, so I'll just begin with the path to 5G. There is actually, there are certain there's this one standardizations body that is known as 3GPP, Generation Partnership Project. This is the entity, and this is the standardization body which is responsible for all the mobile, for all construction and development of all the mobile wireless standards, starting from 1G to 2G to 3G to 4G, 4G LTE, 4G LTE advanced, 5G new radio, 5G new radio advanced, and then towards 6G. So what they do is that starting from 1980s, they have dispersed, or they have introduced these technologies in phases in the terms of releases. So as the topic today is from 5G, so I'll start with release number 15, which is the basic fundamental release that was introduced by 3GPP in 2016, the mid of 2016, as a study item, and then as a work item for its implementation. So when the so before projecting into this path of 5G, let's go a little bit back to 4G. That what happened in 4G and what made it necessary, or what mandated, or what are the necessities that instigated and that encouraged for the development of 5G. So LTE, actually, the standardization of LTE began with 3GPP in 2005, where the framework of LTE was actually designed to optimize data throughput and voice over internet, VoIP. You must have heard about VoIP. So VoIP was first introduced in LTE as a as a technology. Then there's a then of course then there's some continuing LTE evolution, some added and additional use cases such as support of broadcast services, then extension to heterogeneous networks, device to device communications, then vehicle to everything communications, and then machine type communications, which was actually bifurcated into two parts, which was enhanced machine type communications and narrow band IoT. So basically, there were some components, some basic features that was introduced in release 15, basically. So I just want to enlighten you by letting you know about the features that were introduced in release 15, so that you can have a very good understanding of how standardization process happens, and how things are included in advanced in future releases for future specification and to incorporate futuristic technologies. So, given the learning and the background from 4G, 5G actually was introduced as a very solid baseline with the first release of was non-standalone 5G. Non-standalone 5G was actually, it was introduced in conjunction with LTE, in addition with LTE, and then later on there was a standalone 5G, which was incorporated as, what do you say, where the 5G core was independent, and there was no need for LTE. So non-standalone and standalone are the two types of 5G variations that were incorporated in or that were introduced in release 15. And there were three very high-level cases for this one release. That is the enhanced mobile broadband. That was one of the features. That was the necessities that encouraged technical society to go towards 5G. It's enhanced mobile broadband. That is high data rate communications. Second is massive machine type communications. Earlier it was enhanced machine type communications and LTE. Here in 5G, it was massive machine type communications. Then the third and the very important one is, even in the real time, is ultra reliable and low latency communications. That is for communications without any latency. That is, you download a movie in a span of 1 millisecond or 2 milliseconds or something like that. So ultra reliable communication means that the communication should be error free, as well as it does not have any delay. That is ultra reliable low latency communications. So in release 15 was designed to be a unified and flexible in consideration of the different performance requirements, such as throughput, reliability, latency, coverage, and capacity. And then it is actually very flexible. 5G was designed to be very flexible in terms of spectrum utilization as well. For your knowledge, actually, I'll tell you that 5G is basically designed for two spectrums: FR1, frequency range 1, and frequency range 2, where FR1 started from 410 megahertz to 7.5125 gigahertz, and FR2 started from 24 gigahertz to 71 gigahertz. So see that this 5G is actually proposed for sub 6 gigahertz band, as well as for millimeter wave bands above 30 gigahertz. So these are the two variations that are that helped, or that's introduced in 5G to be more spectrum efficient, or utilizing the spectrum more efficiently in sub 660 hertz band and in millimeter wave band. So as I told that or the future releases are always advanced than the previous releases. So the same is with release 16 and 17 of 5G, where there were some additional capabilities that were added. For example, the machine type communication support, backward compatible with EMTC, or enhanced machine type communications, narrowband IoT. And then the most important thing in this release was that the incorporation of non-terrestrial networks. Initially, in no standard, satellite communications, IoT communications, UAV communications, or HAPs, that is high altitude platform communications, hot air balloon communications, to provide massive coverage, has not been included in as a standard. Normally, in technical society, in IEEE, you can see a lot of papers on that, but there has to be a standardization body that that needs to standardize it, so that the whole world can be can work on the same page, and can have, all the equipments around the world can be formed or prepared according to a certain specification always. That's why this is the first standard in release 16 where non-terrestrial networks were introduced. NR Sidelink. NR Sidelink is basically device-to-device communication without the involvement of the base station. The direct device-to-device communication, vehicle-to-everything communication, public safety, that are ultimately industrial Internet of Things. You must have heard of IoT. In this Release 16, there's a concept of industrial IoT that was introduced for industries, for sensors, and for use of sensors in industries. So then release 15, 16, and 17 were the preliminary releases, as in 4G also. 4G was initially introduced as release 13, and there was 4G advanced. So here now we are moving towards 5G advanced. 5G advanced is yet not been standardized. It is actually been proposed to standardize by 2024, but I am giving you a glimpse of what could be present in the release 18, because there was a workshop, 3GPP workshop, that happened in just recently 2021, and they tried to discuss all these requirements that could be incorporated, it could be included in the release 18 or the further standardizations of 5G. First is massive MIMO enhancements for both uplink and downlink. Second is the multi-carrier enhancements. We know that there's a technology called OFDM, which was first introduced in 4G. So it has its own demerits and cons. So multi-carrier enhancements to non-orthogonal or orthogonal multi-carrier schemes, for example, for example, GFDM, non-orthogonal multiple access, NOMA, then filter band multi-carrier. There can be multiple numerous techniques that can be helpful in these enhancements. Then mobility and coverage enhancements. That is for sure that in every generation, what we crave or thrive for is always mobility and coverage, high data rate and coverage and capacity. These are the two things that you always thrive for in upcoming generations. Then mobile internet access backhaul. Then, and as I told, that NTN enhancements. Previously, NTN was proposed, and in this release, NTN incorporation of the inclusion of NTN will be more enhanced. It will be included in a more advanced form. Then NR support for UAV and Internet of Things for NTN enhancement. That's very obvious. So these are some of the features that will be involved in 5G advanced by 2024. Now, the same standardization body, and as we are going towards 6G communication, so we anticipate that the first release of 6G will be anticipated by 2030, and that is why even in India and around the globe, people are it's a race race against time, that people are trying to, they make their own standards, as India has already prepared its own standardizations committee. So whatever is not included in 5G, or whatever I'm showing in this slide, if it is not included in the slide, the technologies which will be developed after that will automatically be included in 6G. So that is why by 2025, 28, there'll be the study items, or there'll be the initial studies or research that will be done in 6G, and by 2030 it will be released as a first standard around the globe. So when we say that we want to proceed from 5G to 6G, so there are some use specific cases that there are certain features that 5G entails, that is enhanced mobile broadband, massive machine type communications, and low latency, reliability and low latency. is that we have the technical society have carefully designed a filter which is called as a FIDAS filter, PHYDAS, FIDAS filter. That is a very specific type. So once simple synchronization is an issue, so this is also this concept also provides flexibility in simple synchronization. So all you need to understand is that there's a different filter which is a FIDAS filter, and all and else everything remains same as the concept of OFDM. The FIDAS filter plus the concept of IFFT and FFT and the receiver, obviously. So the previous three, four technologies I discussed about were the technologies that were that are anticipated to be proposed. Still, I said that 5G advanced is still in the development phase of 2020, and it will be available by 2024. So those four technologies are anticipated. So they are already proposed in literature, but they're anticipated to be included in the standards. Now, once we move towards 6G, so see that there's a graph. There's a graph where we move from 1G. There was frequency division multiplexes to 2G to wideband CDMA in 3G to OFDM, introduction of the OFDM for the first time with MIMO in 4G, and then 5G, where enhanced LTE, where I said about the non-standalone aspect of 5G plus new radio, where OFDM can be clubbed with this particular multi-carrier scheme can be clubbed either in centimeter wave or millimeter wave. Centimeter wave is sub 6 gigahertz band. I told you na, that sub 6 gigahertz band and the band above 30 gigahertz, which is millimeter wave. Massive MIMO concepts, then low parity check codes, LDPC codes, and these are it's a, they all fit in the basic communication system block diagrams. So, so this is LT. This is the place we are in. This is 2023, and this is the place we are in. Now we want to project. We want to proceed to this particular direction, where these are all the things that are anticipated and that are in the gossip, in the discussion. They're still not standardized. They are proposed in literature as reviews, as surveys and tutorials, but they are still not standardized. So, what is the future of radio access technology? We have discussed four radio access technologies. What is the future of these radio access technologies? What is enhanced new radio? What is how OFDM can be clubbed with new waveforms or new modulation techniques? And one special category that 6G falls in is terahertz communication that we are discussing about more than 100 gigahertz of frequencies, and then enhanced massive MIMO, ultra low latency communication, and obviously uh, in today's world, AI and ML, artificial intelligence and machine learning, is being connected with everything to enhance the performance. That could be the case. So this is the diagram which is not prepared by me. This is from the industry, from NTT Docomo. Is actually this is what they think as of now. Qualcomm may think differently. Broadcom may think differently. Verizon can think differently. But everything will be clubbed together and they can be formed as a standard. So I think I have given a brief introduction about how standards are formed, how we are trajecting from 4G. We have started from 4G, we have reached till 5G, and we will move towards 6G. So there are some of the key reasons that why we should move or why we should migrate from 5G towards 6G. That is pushing to higher frequency bands. One thing that should be kept in mind is that when we move from one generation to the another, it is it is very evident that we are hungry for high data rate communication, and high data rate communication can be easily provided with higher bandwidths, and higher bandwidths can only be provided with moving towards higher ranges of frequency. So that is pushing the communication to higher frequency limits to millimeter wave bands and terahertz bands, 100 gigahertz, 1 terahertz of frequencies, or 2 terahertz, sub terahertz, 140 terahertz of frequency, something like that. It's like insanely high um, frequency bands. So we'll get insanely high data, high speeds of communications. Creating smart radios so reconfigurable. That this is the point that I'll discuss in subsequent slide. Removing the conventional cell structures. Till date, we understand that there is a cell structure. There's a in wireless communications. You must have read that there is a hexagonal cell structure. Now, people are discussing and gossiping about the cell-free structure, so cell-free massive MIMOs, cell-free massive MIMOs, whatever, depending on the concept of cell breathing. You understand the concept of cell breathing is that uh, if the users are available to the cell edge, there's a signal. If the users are not available to cell edge, then most all the resources are contained to the users which are near to the tower. So the size of the cell will shrink and then the cell increases. So it's a breathing thing. It's a increasing and diminishing of the cell structures. And that is the concept which is being proposed in massive MIMO. So as I said, the 60 will rely on millimeter wave technology. These are some of the bands that it will rely on. Plus, there's a one special category which is called as visible light communication or free space optics that I'll touch upon in some time. So in conclusion, what I'm trying to say is that requirements for 6G is actually we are going for extremely high data rate communication, high data rate capacity for insanely 100 Gbps of data rate. Then 100 times the capacity means 100 times if a current a particular cell is able to connect 100 people, it is 100 times 100. It is maybe 10,000 people can be connected to that. So it's all a very fancy thing. This is all what we desire, but actually what we get is when things get standardized and it is on the plate and it's served on the plate for the industry to prepare devices based on the standards. Then extreme coverage extension, GBPS coverage everywhere, and extremely low energy and cost. That is, we want everything, but we do not want to spend anything. There's a trade-off. Extremely low latency, extremely high reliability, extreme massive connectivity and sensing. So, as I said, only in literature, as gossips, only as for academic research. These are some of the technologies that are being proposed in literature so far as of now in 2023. First is OTFS, orthogonal time frequency space modulation. This is we will touch upon these concepts in subsequent slides. Then terahertz communications, visible at these are actually the two bands of communication, and one special category is intelligent reflecting surface. This is actually one of the research areas as of now. People are aggressively doing research, and there are a lot of IEEE papers that you can find on this particular topic, intelligent reflecting surfaces, because you must have read about the cooperative relaying or relay concepts. So this introduction of this concept has already already masked the concept of relay. They have done a relay. If this is the concept which is introduced, a relay will the days of using relays will be gone. So first of all, I'll just touch upon again one slider just to give you the concept of OTFS. OTFS is orthogonal time frequency space. In OFDM, basically, again, we go to initial classes of signal processing, Fourier transforms. Signals are always dealt in time frequency domain. There was an IFFT modulator, channel and IFFT modulator, and things like that in OFDM. But when OFDM was proposed in 4G LTE, at that time we didn't had the idea like one day we will have very high speed moving vehicles, high speed aircrafts, bullet trains, concepts like that, racing against time, high speed movements in the channel, movements in the cells. We were not, we visioned like that. So we tried, the technical society, they introduced the concept of OFDM. Now the problem with OFDM is that because of its structure of a sync structure, what happens is even a slightest of the Doppler shift will have will create havoc. Will have the interferences from all the other subchannels of the subcarriers. So for high mobile speeds or high Dopplers, concept of OFDM will fail. That is why OTFS was first introduced by Cohere, COHERE, Cohere Technologies in 2017, first time. And it gained momentum because of its qualities. First of all, that the multiple Dopplers are difficult to equalize. That's very correct. And this OTFS takes care of what these two cons of OFDM. And it works in the delayed Doppler domain. Initially, we used to work in time frequency domain. Now, wireless channel has both multipath effects as well as it can be time varying. Time varying is because of the high mobility. So when multipath and time varying, they are taken into frequency domain. So it equates to delayed Doppler domain. So here what happens is that signal coming in time frequency domain is converted to delayed Doppler domain using inverse symplectic fast Fourier transform. And then there's a time frequency domain analysis, and there's a again symplectic fast Fourier transform. Delayed Doppler domain is converted back to time frequency domain and then fetched out. So what will happen in here is that again with high spectral efficiency and high mobility scenario, high spectral efficiency and high mobility scenario is the key for OTFS. This is the only key for OTFS. Why OTFS is actually utilized. Second, terahertz bands of allocation. This is a very beautiful um, a very beautiful band structure where you see that it's a paper from there's a book called Wireless Communications, book called Wireless Communications by T.S. Rappaport, and this is the paper which is written by Rappaport himself, justifying the use of terahertz frequencies for communication in for high data rate communications. You see that frequencies above 10 gigahertz, they are subject to atmospheric attenuations and rain absorption. This is very well known fact. So now, in this figure, what his research said is that there are certain frequency bands that are barred for usage just to protect satellite sensors and deep space observations. And the rest of the frequency bands, these are the frequency black bars. These are the frequencies that are barred for usage, but these are the frequencies that can be utilized in for high data for high frequency communication. See, 260 gigahertz of frequencies, insanely high frequencies. So these are some of the frequencies that are available for usage in terahertz band for communication. But again, you see that there's a concept of path loss. Why path loss? Because then there are atmospheric attenuations and rain absorptions. So this is the complete diagram, and at what frequencies there are maximum absorptions. So given the absorptions, lower rate of absorptions, I think this range of frequencies are best for communication because that will provide less radiation. So this type of research is going on in the world to identify the bands on which we can communicate. We can um, have maximum spectral efficiency in coverage in what bands. Again, second one is visible light communication. So visible light communication is actually initially we all have heard about infrared communication, virtual infrared communication, far infrared communication, ultra far infrared communication, visible light communication, high data rate, ultra wideband, and these are Wi-Fi standards. So what it says that for a very short range of communication, visible light communication can go up to 10 raised to power 8 bits per second or 100 megabits per second, which can be achieved by this particular, these Wi-Fi standards as well. But for short range communication, device to device communication, such insanely high frequencies and in such insanely high data rates were not possible initially. You can see that infrareds were up to 1 meters, and the range over for VLC communication is up to near about 6 meters. And the source I'm quoting is from IEEE itself. So, given the visible light communication, there are certain characteristics that we need to understand, and the difference with RF communication. That is, the bandwidth is actually is unlimited actually, because the wavelength is in the range of nanometers. Millimeter wave communications is that millimeter wave is that the wavelengths were in millimeters. Those were insanely high frequencies, and then in nanometers, the bandwidth will be even more higher. Higher bandwidth will always equate to higher data rates. Then it does not have any hazard to human biological hazards to humans as of we have in RF communication, because H2O reaction to H 2.4 gigahertz, everyone knows there's a lot of molecular absorption. Then mobility is very limited, of course, and an RF mobility is probably, we are actually dealing with higher technology. So visible light communication can be one aspect for research. It is still in the development phase, and so far what I am telling you is the most updated knowledge as of now. So moving on to the last technology that that 6G might entail or might include in its standardization is intelligent reflecting surface. So intelligent reflecting surface is nothing. It is actually what do I say? It is a planar surface comprising of large number of passive reflecting elements. So these are large number of passive reflecting elements. So one signal comes and strikes these elements. So they are reflected back in a particular direction with certain amplitude change and phase change. So what happens is that when the signals can be mimicked in a channel for the different amplitude and phase, they can be propagated in a different manner, and they can be different. Whatever we understand, they can be different channel characteristics in terms of Rician distributions or Rayleigh distributions, whatever we can find. Plus, it can provide virtual line of sight. See that this guy is in the blockage area. So whenever the signal comes in and strikes back to him, so he will feel that there's a line of sight signal coming to him. So this intelligent reflecting surface, what it does is that it creates a very rich scattering environment in here, so that the connectivity in the urban areas with the very dense connectivity increases. The connectivity increases with high data rate communication. For example, if there that we can put high rising towers on buildings for massive connectivity, but this can be one scenario where for example, people moving in Hong Kong or or maybe in Mumbai or something like that, where there are high rising buildings and where it is even difficult to see the sky sometimes. So this mobile tower activates itself for LOS only when your mobile is in direct communication with it. Now, when the mobile is in not direct communication with the with the tower, so you will always get a scattered multipath in at your mobile, and which is not very powerful. So that is when the signals are not powerful. So the downloading capacity and everything will be impacted, and the voice quality will also get impacted. So this is the concept which will improve the massive connectivity in dense environments by creating the rich scattering environment. So this is the idea which is currently being researched upon very aggressively, because all what you have to do is you have to just paste some passive reflecting elements which does not require any power. There's no power consumption required, nothing, and it will just reflect your signals like a mirror, like just reflect your signals with certain amplitude and phase, and you can create a beamforming effect, or you can create a virtual connectivity at a particular place with which is blindfolded. For example, here you can, when this is a dead zone user, you can correct a virtual line of sight. We can have virtual line of sight. Anything we can have, what we can, whatsoever we can do. So it's very easy to implement as well, and it is operated with orders of magnitude lower hardware energy cost as compared to the traditional active antennas. Actually, if you implement a lot of active antennas, so it will cost us more, but it is, as it is passive, it does not require any power, so it is easy to be implemented. So these are some of the qualities of intelligent reflecting surface technology. So far what we have discussed is that how we move from 4G to 5G, 5G to 6G, what are the key drivers from 5G, what are the key aspects that we have considered towards moving towards 6G, and all of this is these, whatever I've told you is an idea. These are all the ideas, and these are very well documented in literature, very well documented in literature, technical literature, IEEE, Swinger, Wiley, whatever. There are a lot of papers in there, but these are the ideas which still needs to be standardized by the standardization bodies. End of story. Unless and until things are standardized, you cannot see the mobile phones working in 6G, in 6G frequency bands as we do right now. We have 5G frequency bands in the mobiles. So the hardware can only be manufactured once the standards are done. Until it's all very good for academic research. So uh, one last aspect in 6G technologies is that, as I told, that there can be integration of technologies. This is NOMA with MIMO, as I told you, self-free structures, then intelligent reflecting surfaces along with MIMO, application specific. So there are a lot of integration of technologies that can be that is visioned, to happen in 6G. First is the non-terrestrial networks with terrestrial networks. For example, you can connect satellite with terrestrial networks in order to have a very good connectivity, because the footprint of the satellite is very large, and there are very well established mobile network on the land. So connecting satellite with terrestrial networks, you will have connectivity on the ground, plus you will have connectivity in the sea, in the space. In the sea, you cannot put towers, so all you need is satellite connectivity only. That's it. So sensing signals with communication, integrating 4C of communication, that is integrating computing, communication, and then caching together. Integrating communication, caching, computing, and control together. Again, there is one more aspect of it. Space ground integrated networks. This is integrated networks. Space ground integrated networks. The paper, there are a lot of papers on SAGIN, SAGIN. Space, air, ground integrated network. So it's a massive connectivity from space to air to ground, everywhere. It's like ubiquitous availability of data. Augmented mixed reality into extended reality, queuing theory with information theory. There can be a lot of immense possibilities that can happen in 6G, and that can be proposed as academic research for the technical society. Correct. So now, what I do is that I'll just give you a glimpse of what I have done in my as my research using the non-terrestrial networks as a particular application of 6G, as a particular application of 6G, that is integrated satellite terrestrial broadcast system. You can see that this work says that there's a satellite which is connected to the terrestrial transmitter as well as mobile receiver. So mobile receiver can have signal Okay, is my screen available right now?
Yes, sir.
Okay, so I'm switching on to the full screen mode. So I've been informed that the link has broken and you guys stopped viewing this particular slide. So what I was telling you that I am giving you a brief perspective of the NTN, the non-terrestrial network, which is actually the vision for 6G. So this is some part of the work that which I have done as my research, and this says that there's a satellite and terrestrial communication between satellite and terrestrial and the ground, and there's a mobile connectivity. So signals to the mobile can reach either from satellite or from the terrestrial transmitter. So both of them can act as an alternative support just to provide ubiquitous or seamless connectivity to the mobile receiver. Another aspect is that there's a hybrid satellite terrestrial broadcast system where both of the signals from both the links are received to the mobile receiver. So now mobile receiver will have the flexibility to choose one of the best signals, or it can combine those both the two signals coherently in order to have a higher SNR. Higher SNR will automatically be equated to higher spectral efficiency. So these are the two aspects that I have done. So what I will do is that I will go through the performance analysis of a certain modulation scheme in this particular system, in this particular scenario. And slides beyond this are going to be a little mathematical. So just bear with me for some time. So this is one part of the signal which is actually which I'm saying that which I said that before that it is actually the concept of digital TV or digital broadcasting, where a lot of audio video programs are or a lot of audio video programs are encoded in a particular program. You switch on to different channels. These channels are nothing but different frequencies. You switch on to different channels, and there are a lot of teletext packets. Teletext packets means that there are a lot of text that runs along with the video. For example, translations in from one language to the another. So there is these all the things they are actually multiplexed as statistically in that statistical time division multiplexer, and then they are forwarded to the OFDM for its transmission. You map it onto an OFDM symbol and you can transmit it. So this is actually that was previously there. But what I did is that in this particular scenario, there was no flexibility for variable bit rate quality of service. That audio, video, and text there are of different data rates. So achieving flexibility in quality of service is different. For if you combine all the packets together and transmit it, so audio, video, and text they will all suffer if there's some burst error in the channel. So the entire data for audio, video, and text will be gone, or they will they all these three bifurcation or all these three things will suffer the equivalent um, effect from the channel. So there's no flexibility of achieving variable bit rate. Second, the sensitivity to OFDM, as I already told that it is very sensitive to carrier frequency offset. That is high Doppler speed if this there. So the entire framework of OFDM will crash, and phase noise. Time slot management is another one issue because you need to have symbol synchronization all the time. So what I proposed was that OFDM should be used in conjunction with code division multiplexing, so that there are a lot of multiple parallel codes for each incoming parallel streams, and these codes are used to spread the signal in the frequency domain. You spread the signal you spread the signal in the time domain, so that you will have a very narrow band signal in the frequency domain. So that is my concept of using CDM. Another thing with OFDM is that there are narrowband channels with subcarriers. So this times dispersion will be easily contained in this narrowband subcarriers of OFDM. So for variable bitrate communication, I am trying to access this proposed technique, and this particular modulator is called OFDM CDM modulator. So again, see that there's a fusion of two technologies. Code division multiplexing is one technology. It is amalgamated with OFDM to ensure um, that my purpose is solved. High data rate high spectral efficiency, good coverage. This is all what we need, right? So this is my concept. So this actually provided me with the flexibility to use variable bitrate communication, high signal to noise ratio at the receiver, and there's no slot management because what we are doing is we are using code division multiplexing. So time slot management is as related to statistical multiplexing is alleviated or it is removed. I'm not using it anymore. So again, now there's an introduction. There's a this is an LMS channel which is connected from satellite to the ground. So the link between satellite to the ground will have certain distribution. As you know, there's a distribution of signals, random signals from between mobile and the terrestrial network. They are a relic or Rice. Now, from satellite to the Earth station, there's a specific channel which is called as a land mobile satellite channel. So this is also a very typical channel because its delay spread is actually less than 2 microseconds. When the delay spread is less than 2 microseconds, so the delay spread is less, so the coherence bandwidth is higher. Or when this delay spread is higher, coherence bandwidth is smaller. And when coherence bandwidth is smaller, so your frequency selectivity increases. So this is the basic concept. So land mobile satellite channel, it's just the literature review. It has started. It has been incorporated, and the work has started in 1985. Until 2003, there was a channel that was introduced, and finally there was a time series model, which is three-state Fontaine Markov channel model, which is actually in the standards. I've picked it from the standard itself because it's a real-time wireless channel. It's a time generative series model, Fontaine model. It's actually included in digital video broadcasting (DVB) standards, and I took it from there and I did my analysis on this. So this, on a very brief, on a very high level, it's just as I said, that's a Fontaine channel model. It's a um, Markov model. So there's from one point to another point, there's a switching probability of switching from um, one phase, or for example, this is a deep shadowing phase, this is an intermediate shadowing phase, this is light shadowing. So switching from one point or the one scenario to the another, probability of there's a switching probability basically. So this is all the mathematical analysis that the conversion of abdi channel models into three-state Fontaine channel model. So this is these are all the mathematical manipulations. That's it, just to fit in the parameter for the parameters for the particular purpose. Again, this is actually this work is actually basically the analysis of variable bitrate multi-carrier schemes for integrated and hybrid satellite broadcast system. So integrated and hybrid broadcast system I've explained. Now I am trying to analyze this OFDM plus CDM fusion modulation schemes. How will it perform in this particular system? Given there's a satellite, there's a terrestrial transmitter at the ground, and there's a mobile receiver. So how will it work in that framework? This is what my purpose is. Now I can see that my mobile can be mobile, that my satellites can be mobile. If it is in a low Earth orbit, it can be very fast mobile satellites. On the ground, my mobile receiver can move, so it can jointly have a very high Doppler effect. And as I said, the Doppler effect is poison for OFD framework. So let's see that how much it is going to distort my OFDM symbol in there. So these are some of the MATLAB parameters that I've taken for analysis. So for example, the sampling frequency of 5.714 megahertz means the bandwidth is 5.714 megahertz. Subcarrier spacing is something. Symbol subcarrier duration is something. These are all the parameters which are actually defined in the standards itself. So I've not touched the very very beautiful fabric of the standards. I've taken it, incorporated, and adopted all these parameters from there itself. So this is the transmitter that I discussed about. This is the SOFDM transmitter, OFDM plus CDM transmitter. I gave the name as spread OFDM because we are spreading the signal in the time domain. That's why. So these are the incoming serial modulated data bits, and this is the Walsh Hadamard or carrier interferometry codes that have taken as the inputs to spread my signal as in code division multiplexing. So the BR performance of OFDM, you see that in the LMS channel, in the satellite channel, you see that the BER is degrading faster than in the terrestrial network. So this says that that given the delay spread of 2 microseconds in the LMS channel, it is quite harsh in the given scenario of integrated satellite terrestrial systems or the non-terrestrial network that I discussed before in S6G networks. So you see that this 0.1327 is a normalized Doppler for a particular speed of for a certain, see that what is the speed? It is 740.51 hertz. So 740.51 hertz of a difference from the carrier frequency is quite a lot. So this is actually not this VR curve is not as bad as it used to be. Why? Because my code division multiplexing, when I am spreading signals in a time domain and collecting the same energies dispersed at the receiver from the different carriers, so it is actually giving me a good SNR, and that is the reason my SNR is not very bad. Or else I could have had an error flow like this. Okay, no matter how much I increase the power, my frequency or my performance is not going to improve. So this is the performance of my SOFDM signals. See that the OFDM is performing bad, but due to my energy collection at the receiver, due to the time disperse the signals, time time dispersion, and then collection of the energy from all the subcarriers, that is actually helping me improving my SNR at the receiver, and that's why this is one of the point of my research that in spite of using OFD in a conventional manner, if we club it with code division multiplexing, this is going to give me a better performance in the same scenario of Doppler effect. So this is all mathematics. This is my transmitted symbol. Mathematically represented, and this is the amplitude. This is the pilot estimation, and this is whatever I've explained. If I have to write it mathematically, so I can write it like this. This is my time spreading, and this is the kernel for inverse fast Fourier transform. So this is how we write an equation. And second, this is actually when the incorporation of carrier frequency offset and phase noise in the channel. Phase noise is basically added at the receiver. Phase noise is nothing but the mismatch in frequencies. If I am transmitting a signal at carrier frequency f1, then due to the mismatch in oscillators, I will have I won't have the same frequency at the receiver to match with it. There's certain delay or there's a certain phase difference in the another frequency, so it will create an error at the receiver. So that error combined with CFO, combined with AWG noise, combined with multipath effects of the terrestrial channel, combined with the multipath effects of the land mobile satellite channel, will give me a very horrible performance. But I made sure that time spreading and time de-spreading of the signals can help me in the improvement of my SNR for better detection. So this is my received signal. So this is my good term, my signal term, and these are all my bad terms. These are all my bad terms. So signal to noise ratio, signal to interference and noise. So if I take the power of this, variance of this, variance of this, and variance of this, so I will have my signal to noise ratio like this. So variance of this and this is clubbed into variance of this. So this is noise variance, this is inter-carrier interference, and this is the total interference from other subcarriers. So this creates a signal to noise ratio. BER is basically calculated as a simple Q function that we all know. It's a Q function of root of SINR, and my spectral efficiency can be calculated using the Shannon's capacity theorem. Channel estimation I have done, and this is nothing new because it's a pilot channel estimation. We send a signal with amplitude of 1, so that in order to tune the taps of the equalizers at the receiver, so in order to get a good idea of the wireless channel, so that when the signal comes, it can be properly equalized. That is what the concept of pilot estimation is. So this is all mathematics. This is actually the error variance of in pilot estimation. For higher bitrate communication, the error is more. For lower bitrate communication, error is less. So this is what it is. Now the main important part is that the BER performance or the error performance of the system is that you see that for high data rate communication, we still have a waterfall type of a curve. We do not have an error flow like this. This is because of time despreading and spreading of the frequency diversity achieved at the receiver. And this is for lower bitrate communications for all the scenarios when there is CFO present, when there is CFO and phase noise present. So this is very classical work that was done and published in IEEE Systems Journal previous year. This is again with OFDM with the higher modulation order. This was with BPSK. This was with QPSK. Pi by 4 QPSK basically, or 4 QAM basically. It's the same thing. So that is the performance with and without CFO and phase noise. This is some of the performance with the OFDM. You see, now this is something which I was talking about. See, this is the error flow. No matter how much you increase the power, your error performance will not come down. We will not have a error-free communication. But when you use OFDM uh, in a planar way, in a very conventional way, when there is absolutely no Doppler effect and phase noise, you see that there's a decreasing curve. When you increase power, you will have at some point of time you will have an error-free communication. So this is what I was worried about, and this is what is the point of my research to take care of this error flow. This is a spectral efficiency. Again, spectral efficiency is calculated in bits per second per hertz. Again, it's just the formula-based thing. When your SNR is higher, you will have a higher spectral efficiency. When an SNR is lower, you will have a lower spectral efficiency. So this was actually published in a Systems Journal. This is now again, this is the fusion of 5G advanced technology, that is FBMC filter and multi-carrier that I discussed before, with the NTN perspective that is actually the concept in 6G. NTN perspective, which is the vision of 6G, non-terrestrial network communication. So for non-terrestrial network communication, I'm having ISTBS, that is Integrated Satellite Terrestrial Broadcast System. And for the fusion of technologies, integration of technologies, I am having spread filter band multi-carrier or filter band multi-carrier scheme as from 5G advanced. The novelty in my work is that I used a different modulation scheme altogether. It's not a conventional FBMC. It is spread the Walsh-Hadamard spread FBMC for time dispersion and expansion. I focused on a lot of focus of mine was towards interference mitigation using time dispersion of signals. That is my entire intent. So again, there's a QAM mapper. It's a QAM mapper is nothing but a quadrature mapper. You send signals in at both sine and cosine. Sine and cosine are 90 degree. There's a 90 degree phase shift. So both the signals are termed as orthogonal. So whenever these signals are sent in a complex form, so they are spread and added, and then there's an extended IFFT. Again, I said that there's a FIDAS filter, or there's a components of the filter, or the coefficients of that filter that are incorporated so as to in order to reduce the spectral leakage due to OFDM symbols, rectangular waves. So this is what it is. So as a whole, this is a combination of it's a combination. It's like a filtered OFDM. FBMC is like a filtered OFDM, and this concept of SFBMC is a spread filtered OFDM. something like that. So in a very generic way, if you can say that. So again, this is all mathematics. This is for the quadrature components QAM के लिए. This is cosine and sine components. This is a Pareto estimation. This is spreading of the signals, and this is my FBMC kernel, or the IFFT extended IFFT kernel, or the modified IFFT kernel, right? So this is what it is. Then there's a millimeter. This is maximum mean squared error equalizer that I have used at the receiver. And then there's an SNR variation where there's a signal energy as well as the bad terms in the denominator. So what do we do with the bad terms? We try to minimize them so that this ratio can be increased. When this ratio increases, your BER gets improved and your spectral efficiency increases. This is what it is. So again, these are very boring and very long equations. So all it gives you is that there's a variance, there's an intercarrier interference, all these intrinsic interference and everything, residual interference and all these things and noise. They all come as bad terms in the denominator. So now, when there are two independent symbols, so by the concept of digital communications, we say that this is the probability of correct detection into the probability of correct detection of the sign, and one minus of this is the probability of error detection. So this is what it is. So again, we take the spectral efficiency using Shannon capacity theorem, and then we take the maximum capacity out of both the streams. Why maximum capacity? Because everything is a random variable due to the channel, and we always use the statistical averages to summarize our results. Again, this is the concept of final channel estimation, a lot of equations, and then for high data rate, bad positioning, or an inferior error performance, inferior estimation performance. For lower bit rate, good estimation performance. When all these is clubbed into one, when everything is clubbed, all of these are clubbed as an entity in a single system. This is the error performance that we get. See that this is a very beautiful result. That is, that for a very high data rate communication, this is 16 times the bit rate, 16 times the RB. RB is the basic data rate. Basic data rate I took was 120 kbps. 16 times 120 kbps, 128 kbps. Then it has started giving me an error flow, even despite my precautions for interference mitigation. I tried to do interference mitigation. This is the point for my further work, where I can use different types of interference cancellation schemes at the receiver in order to straighten this curve, so that after increasing my energy to a particular level, I can think of achieving an error-free communication. So this is one of the results. Then OFDM with conventional FBMC was considered. Obviously, OFDM was a very bad candidate. FBMC was a little better candidate. Why? Because it tried to stop the spectral leakage into different subcarriers. So because of this spectral leakage containment, it is giving a better BER performance. But still, you see that after the BER, after the limit of 30 dB, it has started to increase, and there might be an error flow after that. So this is where my spreading would have worked, and I got a straightened curve somewhere. Again, this is a very conventional OFDM, simple technique of OFDM with classical modulation scheme, OFDM with 4G. The last part of my work is a hybrid satellite terrestrial broadcast system. Hybrid satellite terrestrial broadcast. So what did I say? I said that my mobile receiver can receive signals from both satellites as well as from terrestrial repeater or the relay terrestrial relay. Both these signals can be combined using the maximum ratio combiner if they are coherent, or if I make them coherent in phase. Two frequencies or two signals can be added together and can achieve a good amplitude if they are in phase. So in order to bring them in phase, we need to multiply. So we need to do a certain signal processing at the receiver, and that is the concept of maximal ratio combiner. So source, there are a lot of relays and destination. So what happens is that this is basic transmitted signal. So there are two types of there are two modes of communication. In phase one, the source will relay the signals to the to, will pass on the signals to the relays as well as the destination. And in the second phase, this is basically the concept of cooperative relay, because there's a lot of cooperation from the relays. They are actually complementing, or they are actually what do you say, that they are forwarding the signals to the destination, source signal to the destination. So phase one is limited to this, and phase two is starts from the relays communicated to the destination. So this is again the mathematical representation of the signals in phase one. With this is the I-50 kernel, and this is spreading. This is again the pilot estimation, amplitude for pilot estimation, and this is the energy of the signal, or the amplitude of the signal that is initially used. So in the first phase and the second phase, there are two types of signals in first and second phase. So there, the closed form SINR expressions for the first phase and for the first phase and the second phase are differently achieved. Again, this is the good term, this is the bad term, this is the good term, and this is the bad term. So the bad terms, the energy of the bad terms are like this. This is the noise variance, total interference, intercarrier interference. Why intercarrier interference? Because I'm considering mobility. When mobility comes into picture, channel becomes time varying, and when channel becomes time varying, there is intercarrier interference because of the inherent structure of OFD. Again, this is all mathematics, and this is all the different variances calculation. So now finally my BER can be converted in this format. They can be it's a Q function, where the Q function for different relays can be mapped as the multiplication of different components, because they are independently and identically distributed in time. Okay, so this is what it is. Now again, the spectral efficiency, this is all classical mathematics, of digital communication, but with slight tweaking and slightly modifying it to your own purpose. That's it. So this is maximum of minimum. This is the basic concept of cooperative relaying, spectral efficiency, and this is all because of Shannon's capacity log to 1 plus SNR. It's a very simple concept. So see that one important piece of result is that over here is that even if we increase the number of relays, so maximum ratio combiner, if we have a coherent combining at the receiver, so it should have given me a better performance. But in each and every link, there I'm considering my satellite to be moving, I'm considering my mobile to be moving, everyone is moving here and there. So there will be a lot of high Doppler effect in each and every link. So when there's high Doppler effect in each and every link, so that all these losses are compensated with my frequency diversity gain achieved at the receiver in the presence of CF1 phase noise in each link. Because of each link, CF1 phase noise in each link. So this is one piece of result. And again, OFDM, I took my comparisons with OFDM because it's a very classical technique. It's already present in the standards. So whatever we develop in literature, whatever we contribute to academic literature, it should always be in reference to what is already present. So this is already this I've compared with the classical OFDM scheme because it's already present so far and it is standardized. That's all. So you see that this is an inferior performance of OFDM by default of its classical architecture. So I think I have given not a boring lecture, but I have reached to the end of my slides. So future work in the domain of NTN could be the I have considered a single beam scenario. If I can use MIMO, there can be a multi-beam scenario. Obviously, I can club MIMO with my work to increase my spectral efficiency and data rate. Utilization of millimeter wave band remains to be worked. Then going into a little bit of electronics, there's a traveling wave tube amplifier. What is the problem of an amplifier? Is that if the signal is in the linearity range, then only it is okay with the amplification, or else when it goes in the non-linearity range, it's an issue. So what will happen is that signal to noise ratio में जो है SNIR, interference plus noise, this term again will be added, one more term will be added to the denominator. So it will reduce my SNR. When my SNR reduces, so spectral efficiency will reduce and PER will degrade. Last one is the non-orthogonal multi-carrier schemes such as GFDM, universal frequency multi-carrier. Then in ISTBS, all these, there are a lot of modulation schemes that are still available in literature to be accessed or to be assessed or to be analyzed in these particular NTN networks. There can be a lot of NTN networks related to UAVs or HFPs. Many things can be done. Now, there can be certain use cases for futuristic 6G. For example, all these releases can go into the automation industry. Terahertz communication is unexplored. Internet of many things is unexplored. Security and privacy. This is a classical. I tell you, this is a classical area. If students start to work in this particular area, they are going to easily find jobs in industry, because everyone is thrust with privacy and security of data security, because of so many technologies evolving and people adopting so many technologies. There's a gap for security and privacy even in big data, artificial intelligence, incorporation of artificial intelligence and machine learning algorithms. You know, it's very difficult to secure your data sometimes, and that is why people are now looking into quantum communications or quantum key distributions to secure the data, or uh, going from wireless communications, entirely shifting their focus to quantum communications. Quantum communication could be one aspect. No one is discussing about it as of now, but it could be a very potential area. Of course, cell-free networks. I said the concept of cell breathing and extended coverage. This is always what we desire. So this is what I have for today. I think I have made my uh, lecture impactful for the listeners, and I hope some of the PhD students might have, or research students will be benefited from it. Thank you very much, and I am open for questions or queries if you have. Please go on. I'll be very happy to answer any of the queries you might have. Or if you do not have any questions, I will just motivate you to work in the domain of security and privacy, as well as take a leap in quantum communications, which is actually not of it's a futuristic technology. And there's a lot of concepts of quantum key distributions or quantum entanglements, which you need to understand. And even IBM, the company IBM, they are very much focused into this perspective of security features in data communication. So we can one can look into that as a career. Yeah, please go ahead. We still have 15 minutes.
Hello.
No, of course. We are always, as I told, we are hungry people. We always we are thriving for better capacity and coverage. You see that there are a lot of connecting devices coming up, a lot of IoT devices, a lot of if you see that mobile industry or the handsets what we have, they are increasing in a tremendous fashion, right? So there are a lot of connected devices in the network. Even if you say that this connectivity to everything, even your refrigerator, microwaves, and everything, they'll be given an IP address, or if they can be connected to an internet. So always a revolution is always necessary ahead in order to in order to what do you say, fulfill people, in order to provide good communication to people, or provide good connectivity to people. Everyone should be connected every time, everywhere. This is what the motto is, right? So of course there are environmental hazards. Yeah. So I'm saying that there are a lot of environmental hazards as of now, and we need to solve them. This is our social responsibility. As I said, that we can go for more greener communications, more power efficient systems, which can utilize more power, more less power, whatever it is. So these are all different topics for research in future. So that's why we need to migrate from 4G to 5G, 5G to 6G, 6G to 7G, and ahead. Any other question?
Hello.
Yes, please.
Uh, Good afternoon, sir.
Please go ahead.
Sir, I have questioned that according to the 6G generation, 6G exposure to the high frequency radiation, there are so many medical or as well as other conditions to be affected on negative impact on health. Then how can we have to just conflict to them?
That is a very good question. But the thing is that going into RF communications with very high range of frequencies, so there's a trade-off. And medically, if it is a little bit, and for example, there was a lot of hue and cry, there are a lot of hot problems with the 5G incorporate हुआ था. There the frequencies will the radiation is actually very hazardous for human beings or something like that. So these things are there. Absorptions, molecular, or the liquid absorption is there, but we need to find the way out so that we can go for more greener communications, and to to develop technologies in such a way that given the limited number of resources, we can achieve the maximum out of it. There is a problem. There is actually a problem regarding to that, and that is why जब standardizations committee बैठती है ना, तो उसमें there are a lot of people from the government, from the medical background, and a lot of people from the legal background. Everyone they sit. It's not an easy process to standardize a thing, but once standardized, they take care of all these problems in terms of legal problems, medical problems, or a lot of technical issues and everything. To take care of all these things.
Yes, sir. But according to this, most effective impact is on the health.
Yes,
So
yes, yes. And it is slowly increasing because the radiation level is increasing in the environment. Yes, it is. But again, what is the demand in the market? That is what the industry will try to fulfill it first.
yes, sir. Okay, thank you, sir.
Thank you. Thank you, Pushpenji, and it was my pleasure to speak to the students here. Thank you. Thank you. Thank you very much.